Hello everyone, welcome to the 3D Scanning and Motion Capture lecture. Today we're going to talk about surface representations. So in the last lecture we had a bit of a longer lecture and we mostly talked about what is 3D actually. We talked about point clouds, voxels, polygonal meshes, parametric surfaces, implicit surfaces, and I gave you a pretty high-level overview of what each of these things are and where they might be used, but we didn't go into a lot of algorithmic detail, which is what we're going to do today in a little bit more in depth. We also talked in the last lecture about different scanning devices, and mainly we talked about depth tensors. We talked about all various devices, how we can acquire this kind of 3D data, and most of the time these devices, they're going to give you a point cloud. Could be in form of a depth image, but could be also in form of an actual point cloud, for instance, from a laser scanner. And today, one of the things, or one of the transitions we want to make is, we want to basically think about, well, we have these point clouds, how can we represent surfaces to begin with, and later how can we acquire or compute these surfaces from the respective input point clouds, because most of the time we only have point-based samples when we do 3D scanning, but in the end of the day we want to get into some form of surface representation. So this is where we're going to continue today. So we're going to go into a little bit more depth what surface representations are, how we can possibly store them, how we can compute them, and then later on also how we can basically do surface reconstruction, for instance, taking a point cloud as input and then using or computing a surface representation as output. So if we're going quickly back to the overview, a little bit of the overview we've already given you in the last lecture, right? We know we have polygonal meshes, we have parametric surfaces, we have implicit surfaces. We also actually have explicit surfaces and constructive solid geometry. So these two things at the bottom, we haven't talked too much about. They might not be the prime representation for surface reconstruction, but we decided to still add them here to the lecture because we just wanted to see what the contrast is to the other respective representations. So now I wanted to give you a bit of a more detailed overview of polygonal meshes, and the reason why I think, or why generally speaking people feel they're pretty useful, and for what kind of applications people typically use them. So for instance, if you had a look at some of the research we're doing on our website, you will see we do a lot of stuff on faces, for instance. And for human faces, we most of the time, we don't just want to detect a face in an image, but in fact, we want to reconstruct a face, right? From either an RGB images, from a video stream, something like that. And the core here is that we're going to use these representation in 3D in order to exercise control, for instance, in a 2D downstream task, right? For instance, we want to edit a video and we're using basically 3D representation as an intermediate representation to gain control over it. Now, if we're talking about polygonal meshes, most of the time you see something like this. Again, here's an example of a human face, or, well, I guess it's mostly the head. And the idea here is we have basically a lot of small faces, and most of the time these faces are triangles. I mentioned this already in the last lecture a bit. There are certain reasons why triangles is often a go-to representation, because that's the thing what makes modeling a little bit easier in the modeling tools right now, but also it's very much what computer graphics cards like GPUs today use in video games or possibly even for movies. Now, this is a fairly regular mesh, so if you're looking at this close-up here, right, we're actually seeing that this like whole head here has actually a bunch of faces, right? So these are thousands and thousands of little triangles. They basically define the surface geometry of this human head here. Now, one thing what these triangles or what these polygonal meshes are doing, they're basically these piecewise linear approximations. So what does it mean in practice? Well, for instance, if we're having a circle here, right, and we have a single triangle here, right, we're going to get a certain error, and this error, as we're subdividing this whole thing here and getting more and more edges, right? So we have 3 edges here, then we have 6 edges, 12 edges, 24 edges, and so on, right? So we're doubling the number of edges every time we're doing kind of a subdivision step and adding more and more polygons to it, we're getting closer and closer to the actual surface. Now, this error is O of h squared, meaning that we need to actually, we need to always double the number of surfaces to halve the error, right? And this is what we see here. So we go here from 25, 6.5% error to 1.7% and then 0.4%. And it's good and bad in a sense. So the error approximation is not that great. It could be much better, right? For instance, if we had here a quadratic surface or a cubic surface, even we could get a lot of better approximation with much fewer number of control primitives. But the good thing is about the polygon meshes is we can basically have arbitrary topologies. And so we can have donuts, right? We can donuts with 1 hole, donuts with 2 holes and 3 holes and so on. So we can basically model all kinds of geometries. And for the better or for the worse, we can also go ahead and have actually even non-manifold meshes being represented as polygons. So sometimes that's a bit of an issue. So you can actually have the representation is a little bit too powerful in a sense. And you can basically also represent invalid surfaces. And we'll get later to this a little bit when we're talking about cleaning up these polygonal meshes. There's also adaptive refinement. It's kind of like what I said here, right? You can just go ahead and kind of subdivide these ones. There's different subdivision schemes. I'm talking only about the subdivision schemes here. I'm not talking about how they're being evaluated. So you can also go ahead and basically use subdiv surfaces. This is actually a looped up subdivision, for instance, will do. But you can also just go ahead and take the triangles and just subdivide the triangles following a subdiv scheme, but still treating them as a polygonal mesh. One thing maybe to notice here, if we're going quickly back here, you actually see that this looks pretty smooth. Often what happens is, like, the surface here is just a piecewise linear approximation, but what you can do on top of the surface, you can actually define surface normals in order to achieve smooth rendering. So the surface is kind of piecewise linear, but you can hack the appearance in the shading later on when you render it by having normals on top of it, right? So this one you have one level of more continuity here. Okay. One thing I already mentioned, modern GPUs, they are really good at rendering polygonal meshes, and they're typically using triangle meshes. There's of course other rendering primitives, like some graphics cards actually can do hardware rasterization also of points or lines. But for the most part, the consumer hardware, like the NVIDIA GeForce GTX series, for instance, they are mostly doing triangle rendering. And any other polygon you're going to feed in is going to, at some point in the rendering pipeline, is going to be converted to a set of triangles. Okay, one thing that is really important here is to realize how fast modern GPUs are actually at rendering. And this is actually quite impressive. So if you're thinking about what happened here historically, so traditionally speaking, you had a computer, right? A computer had a CPU, and the CPU did all the computation for you. But now it turns out that for rasterizing polygonal meshes, you can have a bunch of hardware units that are pretty good at this rasterization thing, right? Like, for instance, in rasterization, you typically use a scanline method. I'm not going to go into all the details here, but this scanline method you can basically implement fairly quickly on a GPU, and you can parallelize the rasterization of the triangles very, very quickly. And so from a historical context, right, like people have, or like the industry, basically added specific hardwares, namely GPUs, starting in the 90s, to consumer desktop computers, practically to play video games for the most part. And that actually took off quite a bit in order to speed up the rasterization. And since then, we have seen a massive development on graphics cards. If you have a graphics card, you also notice they are fairly pricey right now. So like these cutting-edge state-of-the-art cards from like NVIDIA AMD, they're like at least $500, if not like $1,000, $1,500 or so, right? But these ones are actually massively parallel compute units that are specifically designed to do polygonal rasterization very, very fast and efficient. To give you a bit of a hint here, So I tried this out on my own GPU. I don't have the latest one right now in my desktop here, but for instance, my old 1080 GTX registers about 2 to 3 million polygons in about 0.2 to 0.3 milliseconds. I did a bit of texturing, a bit of shading on top of it. So this is maybe not the best benchmark, but I just wanted to give you a bit of a magnitude, right? If you have 2 to 3 million polygons, that's quite a bit, right? So this mesh that you see here has maybe I don't know, a few thousand, maybe tens of thousands max, but typically a few thousand, I would say. So if you have a modern game level or so, you have to rasterize, you probably have a few million polygons, and you can render this basically in 0.3 to 0.2 or whatever milliseconds, right? Okay. Yeah, I already mentioned, so this is really cool. Graphics cards are really awesome. They can do a lot of things right now. One thing I mentioned already is the polygonal meshes is a collection of polygons, but the problem is they can also be broken in a certain way, right? So you can also define stuff that is not really a valid surface. So for instance, if you're looking here, right? So here we have kind of one face that goes beyond the other surface, right? And this is kind of a broken representation. This is not something that could happen in the real world very easily, because you would expect this is kind of a closed surface, right? And this is kind of interesting when you're cleaning up meshes, and we're going to talk about this a little bit later in this lecture. These kind of artifacts, they often or sometimes appear based on certain reconstruction methods, especially when you're taking like point cloud data that is unstructured. So you have to be careful when you're doing these kind of things. Okay, so one term I already mentioned, and one term is a manifold. And of course, there's a lot of math terms behind it. I don't want to go into all the details, but I just wanted to roughly explain what I mean when I mean kind of a well-defined surface, and that's what I would call a manifold. So when the intersection of two triangles is either empty, it has a common vertex or a common edge, right? So basically, this intersecting the surface, what you've just seen, would be a non-manifold mesh, right? And this is something we typically don't want, because that's not something that a real surface would actually represent. In addition, the edges, they have to be one adjacent triangle, which is basically a border edge, or two adjacent triangles, which would be an inner edge, right? This here would be an open, in this open fan here, you're having a border edge, and here these edges here, these are basically inner edges. But what's basically not possible is that you, in a sense, you had like a third triangle here that is intersecting with this edge or sharing this edge. Then it would be also non-manifold, right? And then for a vertex, it's pretty similar in a sense. A vertex is either built in a single open fan. This one here, basically, this is an open fan, so you have this vertex here in the middle. Or it's a closed fan, so you have a vertex in the middle, and this is going to be closed. But basically, again, what's not possible that you would have like another triangle where the tip of the triangle would share this one vertex, right? This would also be a non-manifold mesh. So let's have a look at a few examples, what this means in practice. So a few examples of non-manifold meshes is basically, this is what I just described. You have kind of two closed fans, and they share one vertex here in the middle. This is a non-manifold. If you have two open fans that share one vertex, this is a non-manifold. If you have three triangles on one edge, that's a non-manifold. Or you have basically intersections of triangles. If you have one triangle and you have another triangle within that triangle, that's also a non-manifold mesh. And this is pretty important, again, to know when we're doing reconstruction. These cases we typically want to avoid. But unfortunately, polygonal meshes can actually represent them, so we have to be careful when we reconstruct them, and or if we have some of these broken meshes, we can figure out how to actually make them manifold meshes and clean them up accordingly. Fortunately, we can at least detect it. What to do with it is another question. Okay, another thing what people often talk about is topology versus geometry. And topology is basically what you have as a representation of the surface, right? So for instance, the donut versus not a donut. But these two things, for instance, they are topologically equivalent, right? They're both basically planes, but they have different geometries. Same thing with the donut. If you have a donut with one hole, right? But you have different donuts, all of them would have the same topology. They're topologically they're equivalent, but they have different geometry. And here, right, the topology here is basically the vertices here, like this graph basically, and the edges. This is the same here, right, between those two, but the geometry, i.e. the absolute sizes of each of these primitives, is actually different. So the geometry is different, but the topology is equivalent. This one here is the opposite. This one here is geometrically equivalent, but the topology is going to be different in order to represent the same surface. One thing here to clarify, often what you see with polygonal meshes is this issue what I mentioned, is the representation is a little bit too powerful, so you basically can represent the same geometry with different topologies, right? So you have different triangulations for a specific surface, and that's an issue, of course, right? We need to reconstruction because that means you have multiple solutions to reconstruct a surface, meaning that you have to deal with it in the reconstruction pipeline. Okay, so by no means is that a comprehensive summary right now. Specifically in math, in computational geometry, there's actually a lot of research that is going on into these directions. I don't want to go into this one right now. What's a little bit more important for us is more the practical applications. For instance, how do we even store a polygonal mesh? And a very common way to store polygonal meshes is we simply have something like a shared vertex data structure. So what does shared vertex mean? Shared vertex means you have basically one list of all the vertices, and then you have a second list that says how do you connect these vertices in order to form faces, right? Okay, and what that means is basically the vertices, they can be shared across multiple faces, which in practice is often the case. So if we're having here a vertex list, so this like polygon here, sorry, this polygonal mesh here has 1, 2, 3, 4, 5 vertices. These 5 vertices, they have 3D coordinates each, right? And now we have a face list that says, oh, which vertex here that you just have an index is forming the respective faces. So if you have face 0 here, that says take vertex 0, take vertex 1, vertex 2 out of this vertex list and form a triangle out of it. So if you have here an entry with 3 indices, that says that's going to be a triangle. If there were 4 indices, that would be a quad mesh, would be a single quad, right? So if all of them would have 4, then it would be a quad mesh. Okay, so here we have, in total we have 6 faces, right? Each face has 3 indices, meaning that they're all triangles. And as you see, some of these vertices are being shared. So for instance, face 0 uses vertex 1, and face 1 uses also vertex 1. And let's make clear what this means. So we have here basically these 5 vertices. These are these pyramids, right? So we have, here's the 0th vertex, first vertex, second vertex, third, and fourth. And now if we look at face 0 here, that's sorry, it's a little bit confusing. So face 0 is this face, sorry, get it right. No, for face 0 is this face here at the base of the pyramid, right? So what it does is it connects vertex 0, 1, and 2. It's that one, and that one. These are forming a triangle. And then the next face is the other face at the base of the pyramid. That's this one here, and so on, right? And this way you can basically define your polygonal mesh by simply storing a vertex list and a face list. Now, this is pretty much the standard file format, or the standard data structure for all of the standard file formats. So one thing you will often encounter is something like OFF files, OBJ files, STL files, imply files. These are common things. They can be stored in ASCII, but some of them can also be stored in binary. But in principle, they always have the same property. You have a vertex list, you have a face list that defines your mesh, basically. What's important here is if you're implementing this yourself, again, be aware that if you have here faces that define basically this is an index axis, right? So like this basically makes a lookup here. The standard thing when you implement this yourself is you're going to get a bunch of segmentation faults when your index arrays are actually invalid, right? So basically all of these indices here, they actually have to exist in the vertex list, otherwise you're having a little memory access for the most part, yeah. So you have to be careful here, right? So checking the validity of the file if you write your own loader or so is actually quite important. Now, how does it look in practice? Here's an example of a cube. This is just a shared vertex structure. This is an OBJ file. This is something that you could load with MeshLab, for instance. Oh, I didn't write this down. MeshLab, for instance, is a very good tool, for instance, to visualize OBJ files, apply files, and you can load these files with it. So if you have a file like this one, you see here, there's a bunch of vertices. They have 3 coordinates each. And there's a bunch of faces that define how these vertices should be meshed together and form respective triangles. Yeah, maybe one part of the homework could be save this file as an OBJ file, download MeshLab, and drag your OBJ file into MeshLab and visualize it accordingly, right? Okay, same thing could be done with apply file. Similar idea, looks a little bit different in a header, but same idea. You have a bunch of vertices here. Here the indices, here the apply file is a little bit different. They have this 3 here that says, oh, there's now 3 indices coming afterwards, meaning this is 3 means it's a triangle, and 0, 1, 2 are the respective indices into this vertex array, and then this goes on for the other ones too, right? Apply files are a little bit more powerful in a sense that they can also be encoded as binary. So basically this header can go ahead and say, oh, instead of using a property list as uchars here, you could basically go ahead and define this as a binary encoding as well. So you wouldn't be able to read it as a human anymore, but you can significantly save some storage, right? Just again, for clarification, storing this one here as an ASCII is super inefficient because every single character here is basically 8 byte. Sorry, every character here is 1 byte, it's 1 char, and that is of course very, very inefficient, right? So instead you would store simply the float values or so, then you have basically, instead of these numbers here, you have basically 4 bytes per float, and you just streamline it accordingly, right? Okay. Yeah, these are basically polygonal meshes. This is probably the standard file format, either OBJ or apply or off or so is one of the file formats that we're going to deal with in this lecture. And this is the thing you will encounter a lot when you're talking about 3D reconstruction. I still wanted to share a few other things. One data structure that people use is half-edge. This is a very powerful data structure. So the idea here is a little bit different. So the idea here is you want to make geometric queries very easily, right? For instance, oh, traverse my fan, or tell me what is my neighboring face. Find all faces that are around one vertex, stuff like that, right? These kind of operations, they cannot be done that efficiently with a shared vertex data structure, right? So if you're looking back here, right, like you have to basically, in order to have any of these operations that I just said, you basically have to always search through the entirety of the file to just find, oh, what's my neighboring face, or what other faces use the same vertex and stuff like this, right? So this is very difficult, and this is why half-edge data structures are very good for these geometric queries. And the way this is done is basically, you basically store, as the name says, as half edges. So you have an edge entry. This is an edge IDE, right? You say what's the end vertex. So like this edge here, E, right, has an end vertex here. It has a next edge. This would be the next edge here. And it has an opposite edge here, which would be this E opposite. And it has a face to it that is attached to this edge here. Okay, so the idea now here is when you want to say, oh, give me my neighboring face. So you can just have a query and say, E, find the opposite edge, this one, and then from the opposite edge, it has another face, which would be this face, right? And so on. You can also traverse around a face, which is E, E point next, E point next would be here, and then you would go basically back. So you can traverse this around. So this is very nice to find geometric queries, to traverse basically the data structure here. Yeah, the vertex idea is very clear, right? The vertex idea has basically, it's an index, and it also has an index of one incident edge, right? If you have one incident edge, it's very easy, then you can get one edge, and then you can traverse around here, you can find the opposite one, and so on, right? And for face IDs, it's the same thing, right? For faces, you just also store one edge, and once you have one edge, you can figure out all the edges around it. So this data structure is really around, defined around the edges, and you can basically use that to traverse this data, the mesh very, very efficiently, and you don't have to go and just do a linear search through all of the entries in the vertex list, for instance, right? I should say, well, let's have an example first, maybe. Okay, let's have a very concrete example here. So here we have a vertex list, we have an edge list, and this edge list basically, if you look here, right, the edge list here has basically an end vertex and an edge. These are the important things here, right? So well, let's talk about the vertices first. These are the vertices. Actually, this should be V0 to V5. We have here the edge list. Sorry, this one is here. It's actually is directed edge. This one was half edge, where you have all of these pointers, and now there's a thing which is called directed edge, which is a little bit simpler, which says, okay, here we have a vertex list, and then in the edge list, you basically just say, I have where is vertex 0 is here. You're gonna have here an edge E1, right? Sorry, you have here the edge E0, and E0 basically says this here is 1, and this is my neighbor, which is going to be 0, right? And so on. And this way you store all the edges in it. I should say this directed edge data structure is only one example. This is why I had to first look at it. There's actually a couple of different combinations here. There's even combinations of half-edge data structures. Sorry, there's even data structures that are not just half-edge, but they are quad-edge, and so on. There's different data structures that basically store more pointers and connectivity to the respective neighboring or opposite faces, edges, and vertices, and so on, in order to make the traversal even easier. So it's basically a bit of a trade of how many pointers do you want to store, how complicated is it to keep this pointer structure in place, and how easy is it to traverse the respective faces. So if you're going back quickly, this here is basically the reference of OpenMesh, and they implement this half-edge data structure this way. And you can use that, for instance, in order to load some data. This stuff will convert it into a half-edge format, because most of the time, again, the formats like OBJ apply file, they're just shared vertex format, and then you can convert it there, and then you can start traversing the respective face. So if you want to do any options, any queries or so, then these data structures are pretty good. But again, this is just one of the examples. There's actually many more, like quad edge is another good example. I haven't even covered this one here. This is something that I have used for a while. It takes a little bit to get used to it, like how do you basically traverse it, but it's basically a set of pointer structures. So if you're used to like linked list in a sense in like C or C++, this thing will be very intuitive to you, because you just say E point next, E point next, point next, then you're here, and E point next would be again the original one, and so on, right? So I don't want to like make this too complicated. I think this is something you might want to look up, have a look at this documentation here of OpenMesh. This is a very good example how this is implemented in practice, and it might be pretty useful if you want to do geometric processing operations. Okay, let's talk a bit about explicit surfaces. Right? This is something we haven't talked about in the last lecture. An explicit surface is essentially, you just have an explicit function, right? So you just say every value y is defined by f of x, right? So f of x is equal to y. And for instance, if you just want to have this line here, you just say m, which is the slope, times the coordinate where you're inputting it, plus a constant. This is defining, it's just very straightforward, right? It's just the line equation. This is an explicit surface, because for every point x that you're feeding in, you're going to get y as an output, right? This one is relatively straightforward, and it's very easy to define a surface like this also in 2D or 3D. So now what you can do is you can have an explicit surface rather than a line, which is basically you get x and y as input. So for instance, here this is x and y. So this goes from R2 and it maps to a height in this case, which is this R here, which is like the z as an output. So for every x, y, you know what the respective height here is, for instance. So the surface is just simply defined by the 3D coordinates in a sense. If you want to sample the surface, is x, y, and f of x, y, right? So this is an explicit surface because what you do, you're feeding in values x and y, and from these values x and y, you're going to get a surface point as output. This is super straightforward, and in principle, it's a lot easier to deal with than a polygonal mesh. The big downside is it's super limited, right? You can't do a whole lot with it because in this case, for instance, you're just basically limited for one height value for each x, y location, right? You just can't have arbitrary topologies and arbitrary manifolds with that, which is a problem. And also, if you want to render it with a GPU, you would again have to convert it back to a triangle mesh. But nonetheless, these explicit surfaces are often being used, for instance, in game level designs. So for instance, if you want to use a terrain in a game and you want to model your terrain with a height field, then this is basically for every x, y location in this level, you're just having one offset from the ground. And this is what the explicit function or the explicit surface in this case is defining. I don't want to go too much into detail how to use those ones because that's probably the representation we're going to use the least in this lecture. But I still wanted to mention this because some people have asked me, oh, yeah, what about displacement maps, height fields, and stuff like this? Yeah, okay, these are explicit surfaces. They are often being used in games. But for surface reconstructions, well, I guess they're sometimes being used if you want to do, like from satellite imaging, you want to do height field reconstruction or so on. But they're typically not the number one representation that you would imagine when you're reconstructing a surface from a point cloud. Okay. Let's go to parametric surfaces. So parametric surfaces is kind of is also the terminology is a superset of many different types of parametric surfaces. The high level idea is what you have is you have a bunch of control points, right? These are control points. Then you have surface patches. This is a surface patch. And this surface patch is being defined by a control polygon, which is essentially this whole thing here. It's a controlled polygonal mesh is the whole thing here. And then most of the time you have like one of the faces here, that is the linear approximation, that's the controlled polygon, and then the surface is typically a curved surface of higher order. Okay, so parametric surfaces are often used in design and construction processes. They are freeform surfaces. They're also used heavily in the movie industry, like subdiv surfaces. I think we've talked about a bit. They are heavily being used. They're parametric surfaces. And the core idea, I wanted to just quickly give you a bit of pointers if you want to look them up. So Bezier curves and tensor product surfaces is the most naive thing that people typically use. So when you're taking a lecture of geometric modeling, you will see these kind of surface types or curve types. So the idea of a Bezier curve is you basically have here three control polygons, control points, P0, P1, and P2. And then you have a function f of u in this case that is basically defined by this control polygon that interpolates the endpoints, right? But then it's a higher, in this case it's degree 2 because you have three control points. This is just a Bezier specific thing, but there's of course other surfaces such as splines and so on. But basically you can interpolate this curve, which is then defined by these points. And now you can also do this whole thing in 3D. So basically out of this curve, we can make a surface out of it. So the idea is we can have this Bezier curve here. We just have three of these Bezier curves. And now what we do is we have another curve, so to say, that connects points on these three curves, and that's then a surface, right? Because now what we do is we basically say we have f of u and v, so u is this direction on these first curves. Sorry, it's the parameter of these in this direction here, and then the v parameter would be the parameter on this curve here, right? So this is called a tensor product surface. These would be, in this case, these would be Bezier patches. And the idea is basically that we're first stacking a bunch of these surfaces. We're stacking a bunch of these curves, and based on that, we're having on the interpolant on the interpolating function of each of these curves, we define another function the other way in the orthogonal direction, and then we're obtaining this tensor product surface. What you see here, again, I don't want to go into too much specific of how Bezier curves are defined and how you evaluate them. Again, there's geometric modeling lectures, but I want you to be clear, okay, this is a parametric surface, and I want you to be clear about how you evaluate them. So basically, you would go ahead and evaluate each curve here first across the u direction, and then you have this other curve based on the interpolating function across the first curves, and then you have the v direction you evaluate. Okay. Yeah, so basically we have this parametric form here, right? So typically you have a function f of uv that goes from R2 to R3. This is what we've just seen here, right? This is these points all live in 3D space, and the input here is a 2D parameter domain. And so it maps this 2D bounded domain to some sort of 3D surface. Bezier curves I have just described. B-splines, you can do the same thing. NURBS can be more complicated. They're kind of the generalization of these. And yeah, in practice, this looks something like this here, right? And yeah, so they're being heavily used for geometric modeling as well. There's a lot of mathematical details in there. Often what you see is when you're talking about Bezier curves, bicubic is often people use. So you basically have C2 continuity across the surface patch. Same for B-splines. Bicubic B-splines are very common. Splines are also used as curves, actually, not just as surfaces, which is kind of interesting. So yeah, this is something, if you're interested in these areas, I would recommend take it, look into these surface definitions, or there's also specific geometry processing or geometric modeling lectures that specify with this, deal with this a little bit more. Okay, yeah, what's the advantage here? Parametric surfaces, they have higher ordered continuity because they're higher order functions, basically. Downside is you can't render them directly, so when you want to render them with a GPU, you always have to convert them back to a triangle mesh if you want to rasterize them, for sure. Funny enough, you can actually ray trace Bezier curves directly. So you can go ahead and have a Bezier patches directly, so you can have a ray Bezier patch intersection or a ray B-spline intersection. This works. This is kind of interesting and typically leads to some sort of optimization problem. It's not so straightforward, but it's mathematically, I think, kind of interesting. Okay, let's talk a little bit about constructed solid geometry. This is also maybe not that much what we're going to use in later on reconstructions, but I think it's pretty important to know what it means. So the idea is basically the surface is defined as the boundary of a solid object that you start with, and then you have a bunch of Boolean operations on top of it, right? So in this case, what you have is, for instance, you have this cube here, then you have this sphere, and you're saying remove everything from the sphere volume from the cube, and you end up with this one, right? Or you can have the inverse, so you can basically just take this part that you just carved out. Right, and with these kind of Boolean operations, right? So right here you have sphere intersection with box, right? Minus some other primitive, the union over some other primitive union and some other primitives and stuff like this, right? So basically you have, by the way, this one is this part here, right? So this surface here is basically defined by the Boolean operations of all of these individual subprimitives, and it's kind of cool. I mean, this is being also used for modeling a lot in design and construction. It is relatively difficult to model organic shapes with it. So you know, it's sometimes a bit counterintuitive how you do it. It is actually used for reconstruction. So there's well, sorry, let's first talk about how this is used in modeling. So this is what people do here when they model this kind of stuff. So there's, this is Onshape. It's a yeah, this is basically a way how you can relatively quickly obtain some shapes. So they have certain properties, but the modeling flexibility then is a little bit limited and restricted. I wanted to also say that you basically can use constructive solid geometry as a reconstruction problem. There's one paper I mentioned here, this inverse CSG. So CSG means constructive solid geometry. And the idea here is that basically you have the CSG kind of grammar or program, or whatever you want to call it, that defines what operations you allow. It serves you as a regularizer in order to do the reconstruction, right? So if you had a point cloud as input and you wanted to reconstruct something, you kind of want to know the CSG tree that figures out how the respective point cloud would be created. Now, it's very good in a sense that the CSG operators, they provide you a great regularization, so you don't get like noisy surfaces or so, right? The big downside is, of course, it's super complicated to reconstruct this because this is typically a mixed discrete continuous reconstruction problem. So if you've ever dealt with discrete optimization, not easy, right? It's very complicated. It's all like, I mean, nothing is convex, obviously, so very difficult to optimize for. Lot of bad solutions, of course, and the solvers are super slow in the most part. But it does exist, right? People use Metropolis Hastings methods and so on to do that, but it's not so straightforward to do in practice. Okay, now let's talk a bit more about implicit surfaces. That's something I feel we're going to talk a little bit more about. Because implicit surfaces, that's the one thing that is often being used for reconstruction, especially in the methods we're going to talk about. So just a quick reminder, like mathematically, right, if you have an explicit function, that means f of x is equal to y. So at every x position, you know what y is. And an implicit function is like when you have x squared plus y squared minus 1 is equal to 0. When you have this equal to 0, that says, oh, the surface is implicitly defined. And this is something that we often use in the context of surface reconstruction. So for instance, like RGBD reconstructions, this is specifically what we're going to look at in the next lecture. There's this famous Curlis and Levoy paper from the 90s that basically defined this volumetric fusion. There's kinetic fusion or voxel hashing and these kind of methods. Again, we're going to talk about these in the next lecture. But I just wanted to give you a heads up. So if you basically take a Kinect and you move the Kinect around, and then you want to get a surface out of it, these methods, they typically use implicit surfaces. And I'm not going to talk yet about the reconstructions. I want to first talk about how the implicit surfaces are being defined, and then we subsequently develop the reconstruction methods around it. Okay, good. Let's say implicit surface, implicit form, right? We just say we have f, x, y, and z, and at every position we map to some value. But this value is not the surface, right? So the surface is defined rather as a level set of this trivariate scalar function. For instance, if this is a distance field here, so this r here would tell you how far away are you from the surface, then the surface would have to be extracted at the level set, in this case the ISO value should be 0, of this trivariate function, and that's where you get the surface out of it, right? Okay, maybe a simple example is the Hesse normal form. This is the standard plane thing, right? So you can define a plane by this implicit representation, so, right? So you just say you have x, y, z as the query input point, minus the point P that spans the plane, and then you say times the normal, this dot product here should be 0. So every vector that lies here, basically, this is this difference here, would be every vector within the plane, times the dot product here should be 0, right? This is the standard Hesse form. Yeah, and in that case, if we're doing a representation like this one, that would basically also tell you, if you think about it, this f here, in this case, you have basically negative and positive values that says, oh, if this function here is negative, you're underneath. If this is positive, you're top, right? And if it's 0, then you're on the surface, right? This is kind of how the plane here would be defined. Often what we're dealing with is signed distance fields. maybe this is not also called sign distance function. Not every implicit functions are sign distance fields, but sign distance fields is one of the ones that we often gonna use and look at. And they, for instance, tell you the distance, how far away you are from the respective surface. This one we're going to talk about in a little bit. But we want to also, I want to quickly share a few other ones, right? There's a bunch of different scalar functions that you can use instead of sign distance functions. So you have the scalar function that says f of x, y, and z gives you a scalar. This scalar could be a density. It's like this occupancy grid with floats, basically, that tells you this is a density instead of an occupancy. By the way, density is super important nowadays because in this whole new rendering field, like NERF and so on, this is basically based on densities. It's also an implicit function. We're having heat maps, heat signatures. You can have or distance fields, what we had a while ago. So yeah, distance fields are also often used for soft shadows and so on in games, but we're going to use them for reconstruction. Okay, so what we really care about when we're talking about implicit surfaces in the context of this lecture is how do we actually find such a scalar function, right? So for instance, if you give them a sample points, this is, let's say, from a laser scanner, but this is a simplified version here right now, just in 2D. We want to find, at the moment, we want to find a scalar function that says f is equal to 0 on the surface, right? So the scalar should be 0. If it's inside the surface, it should be smaller than 1. And if it's outside the surface, it should be greater than 1, right? So this is, in principle, what we would like to do. Now, there's many ways how to find such a function. One of the easiest, or well, simplest methods that people have been using is this Hoppe method from '92. And here the idea is basically, you say, well, right, we have a bunch of these points. If we have a query point that we want to look up, we just find the closest point that we map to. And then we're just going to say, oh, we're just going to evaluate the simple dot product. We say, this vector from my current point, dot product to the next surface, dot product with the normal, that gives you this distance value, right? It's actually the same as this Hesse normal form, if you're going back here. Same idea, right? Except this point P here is not always the same, but rather it's going to change depending on where you are, right? Basically, it's the nearest neighbor in this case. You'll see very quickly it's not a smooth surface we're getting here. So it's just a piecewise linear approximation what we're getting. But this is the simplest thing you can do, right? You just find the closest point. You get this point P. You compute the dot product between the normal. If you're on the surface, that means this would be 0. If you're outside the surface, it would mean that you're greater than 0. If you're inside, it would mean that you're smaller than 0, right? It's just basically using a local version of this Hesse normal form based on the closest point P to your respective query point X. Okay, so how does this look like in practice? Well, if we are having a bunch of points here, right, what you would do is for instance, if you're in this range here, this would all map to this closest point here. This is the closest point within this, let's call it a cell for now, it's called a Voronoi cell. This is the closest point that we have. So, sorry, within this cell, this one is always the closest point. In this cell, this is always the closest point. In this cell, this one would be always the closest point, and so on. And now, what you're doing is basically, you're just mapping every point on this plane, and that tells you the distance, right? So if you're here, this becomes bigger. If you're here, this becomes smaller than 0, and this one here becomes 0, right? So what this means is, basically, the surface is defined by this ISO value here. This is the 0 level set here. And if you're in this Voronoi cell, you have this one here defined as the surface. And here, it would be this one. So in other words, according to this method, the local area will always project to the same linear approximation of the surface, right? So it's a piecewise linear defined on the Voronoi diagram of the input. Now, obvious issues, here we're going to have discontinuities on the surface, because suddenly here you would map to this point as the nearest point, then this plane here would define the surface. Right? I'm not introducing this as the best reconstruction method right now, but I'm saying it's one of the simplest methods to do it. It's very straightforward, right? You just say, treat every point locally as a plane in a sense, and then if you're looking for the current Voronoi cell, right, you map to the nearest point and then maps to the nearest plane automatically according to the normal. One thing you will notice already here is that surfaces are defined, or like this reconstruction often is defined by the normals on the points. So it's not just the points we're taking here as input, we're also taking the normals of the points here as input. We'll see this for many methods actually, that the normals of the points are also required to be computed. This is something we're also going to look at, like how do we even compute normals for the points. It's not so straightforward, but let's just assume we have the normals for the points and we have the points. Then we can compute a surface based on this Hopper reconstruction. Okay, let's have a look at an example. So here's a point cloud. If you have a dense point cloud, right, this is also a point cloud, then these are the respective reconstructions you're getting. Looks pretty good, right? Now, if we don't have, so if we have enough points, this looks reasonable. If we don't have so many points anymore, yeah, it doesn't look so good anymore, right? Then you see these artifacts. So then you see this linear approximation, which is not that ideal in a sense. Then you see some discontinuities here. And if you're looking very closely here, so here you see these respective mappings, so right? Locally, this is a plane here, this is a plane here, and so on. And yeah, this is respectively, you would have guessed, here was a point at the beginning, here was a point at the beginning, and here was a point at the beginning that kind of defines these local surface patches in a sense. And this is the respective reconstruction. So it's a piecewise linear approximation. And as such, it depends heavily on the density of the respective points, right? So here we see low density, high density. Here the surface looks great. Here it doesn't look so great anymore, right? Okay, so this is the simplest reconstruction method probably you can think about. It's very easy to implement, and it gives you something, but it doesn't give you a smooth surface. So let's maybe go a little bit further. Now we want to think about how can we add another constraint to our scalar function that should be 0 on the surface points, small and 0 on the inside, greater than 0 on the outside, but also it should be smooth, right? So now we have a few more constraints we have to deal with. And one of the reconstruction methods here is based on radial basis functions. This is a paper by Greg Turk. It's a variation of implicit surfaces. So this radial basis function idea is basically to say, well, now what we do is we're going to say we have a set of basis functions. That's what's called radial basis functions. And the idea is each complex function can be approximated by a sum of simple scaled and translated kernel functions, right? So these kernel functions here are being used. So we have a bunch of these kernel functions. I'm not gonna, so there's typically a lot of different versions what you can use for kernel functions here. You could use a Gaussian, you can use all kinds of different functions. There's many papers that use different functions here. So machine learning people might recognize this. This is kind of like a mixture of Gaussians, by the way, right? Very similar thing, but you can use that also to define surfaces. But it doesn't have to be a Gaussian. I'm just mentioning that, right? It doesn't have to be a Gaussian, but a Gaussian could be one option that is being used here for radial basis functions. Okay, so what you can do here is you basically have a bunch of these basis functions here. And now what you do is you scale each of them and you translate each of them, right? So here what you do is you have the actual curve G. This is our complicated function that we want to approximate. And the way we want to do it is we're going to say we have a sum alpha I times the respective basis function I of x. And then what we do is we translate it also, so it's x minus c. So it's translated and it's scaled respectively. So this yellow function here is now being approximated by a bunch of these local basis functions, right? Okay, and this actually is a smooth function now, right? So this is a smooth function. And the thing what we can do with that is we can say a radial basis function can basically allow for arbitrary complexity. And what we typically do here is we can just say this I here, basically how many of these basis functions are, define the complexity, right? So we can have arbitrary complicated functions being represented in a form like this one. So compared to the previous slide, what we also do is we have a linear term here at the end. In a sense, you could also imagine this linear term would be part of one of the basis functions, but in practice, you always want to have this linear term. But the idea now here is that if these basis functions are smooth, so will be the resulting function f of x. And if you're doing surface reconstruction, well, the idea is what we have to figure out. We have to figure out all of these unknowns of this. So the basis functions are obviously fixed, but the alphas and the c's and these linear terms, they're all being unknown, right? So we just have to optimize for this, for these parameters here, and that defines then the surface or the curve respectively. Okay, so let's make this a little bit more concrete how this would go. Okay, so we have a radial basis function in 3D, right? So we're having here these 3D points as input. We have the alphas, we have a shift here implicitly given. We're using here a biharmonic radial basis function. Again, there's different options what you can use here. This is just one example. And the PIs are the respective sample points that we, for instance, have gotten by a laser scanner, right? X is always the query point, and X is always the points that we are having here as inputs. Now, if we're having our amazing shape here, this is what we have scanned. We have these points from our laser scanner here, right? These are the PIs. Now the goal is, how can we optimize for alpha, b's, and d, right? How can we figure that one out respectively? These are the respective unknowns. This shift here is given by the respective points. X is the query location, and b, d, and alpha are the respective unknowns we have to solve for. Okay, so how do we do it? Well, in practice, f of x should be 0 at the sample points. That one we know, right? So f of p is 0. That's n equations, assuming we have n number of sample points, right? So for every point, we're going to get one equation. It's a, yeah. And then what we have to do is we have to solve this linear equation. A times x is equal to b. I'll show you in a second how this matrix X looks like, but basically the matrix A just contains these, sorry, this is a bit confusing right now how this is being done. But basically we're solving for these alphas, B's, and D's. It's actually, this is not quite right. I'll figure that out later. Basically we have a matrix A, which is the coefficients here. We have an X, which is, sorry, we have an A, which is the definition of these points here. And the coefficients on the basis functions. X is alpha, b, and d's. These are our unknowns, and b are the respective residuals that we're getting out of this term. Okay. All right. One issue that we're having here is this is an undetermined system where we have actually n plus 4 unknowns. Why do we have n plus 4 unknowns? Well, this goes over all of basically, we have this linear part here, so we have more unknowns than we actually have equations. And solving the system will result in a trivial solution if this x vector is equal to 0, which is a problem. So what you do is you typically add more constraints. And we already know what these constraints will be because we've used them before. And these are the normal constraints. So in addition to saying f of p is equal to 0, which is n equations, we're just having additional constraints where f is non-zero. And normal constraints in this case are very straightforward applied. So all you're doing is you just, for every point, you're shifting a little bit in the normal direction, plus minus, right? And you set these target distance values of these points to some plus minus epsilon, how much you have shifted them accordingly, right? So now we not only have these points pi is equal to q, but instead we also now have these plus minus epsilons. Yeah, and this is actually the matrix. So basically we have in here this x vector is the coefficients we are solving for respectively, right? We have two parts of this matrix A. One is on surface points and one of these off surface points that are slightly shifted. These are the basis functions basically. These are the sample points we have. And this is the one here. This is just multiplying with d respectively. And so just you can see what's happening here, right? So this is basically you multiplying this row with this column here, meaning that these are all the coordinates of the points here are being multiplied with this b here, right? This is b. This one is this one here, right? And then what you have is here you have n equations for n points. You have another n equations for n off-surface points, right? And we know all of the surface points, they should be equal to 0. That's what our implicit function should get at the end. And we know that the surface points that are slightly around it, they're plus minus epsilon. These are these off-shifted q points here, right? So we have the pi's and we have the qi's. These are essentially our constraints. And now we are obtaining an overdetermined system, right? Okay, so, and in this case, we use the least squares formulation, of course, right? So ATA times x is ATB. And this is just a linear solve then, right? And we just use our favorite linear solver. By the way, if you don't know how to solve a linear system, please look it up. At this point, I'm expecting how people know how to use linear solves. This is a very common interview question also. This is something you need to know. For all the deep learning guys, if you're going to come up with gradient descent here, that is not a good answer. So you should know something like QR decomposition, LU decomposition, SVDs, and so on. This is how you solve these kind of things. Depends a little bit on how the problems are constrained, how big the systems are, which solver you use, if you use a factorization-based one or whether you use an iterative one. But linear solves you have to know how to do, right? If you don't know it, Google it right away. Okay, so now we have an overdetermined system. Again, it's overdetermined, so we have more equations than we have unknowns. This is where desired. So what we do is we use the least square solution. We have this the normal equation here. So we have ATAX is ATB. We use our favorite linear solver to solve it. And at the end of the day, we're gonna get the coefficients for our radial basis functions, right? These ones here. This is what we want. Okay. At the end of the day, if we have now an input point cloud and we compare the two methods, we're going to see here our input points. They're relatively sparse. This hopping method we've seen before is only piecewise linear. And our radial basis function instead, they are actually much smoother in this case, right? Now you could also argue, oh, this is too smooth and you lose in the detail. Well, there's a few things you can do. You can think about what the shape is of your basis function. That obviously makes a difference. And also the number of points matters, and also the normal information matters, of course. Okay, but let's see the pros and cons here, right? I just wanted, I mean, maybe not the pros and cons. Maybe this is not a competition here. What is the better method? This is more an understanding of what each of these methods will do. So the hopping method is local. It's straightforward to compute, right? You just have query point. You check out what's the nearest point that you've scanned. This gives you this Voronoi diagram. You map it basically to this local patch or this local plane. It's very easy to compute, but it cannot handle any outliers, noise, and it requires quite a few points in order to give you a good surface out of it. The radial basis function is, on the other hand, a global method, right? Because you're solving this global system that considers all points at the same time to fit the radial basis functions to the respective input point cloud. Then this requires solving a linear system, so that's a little bit more expensive to do. But as a plus, you can handle a relatively small set of points. You're going to get a continuous surface at the end of the day. And you can handle like noise and outliers to some degree. I should say this with a caveat because you might have to regularize this a little bit too. And in practice, there's actually a lot of papers how to deal with noise and outliers in these kind of optimization problems. Right? It's actually not as easy. And what I just said is, if you just solve this naively with this matrix, and you have a bunch of outliers in this least square solution, this can also pretty much screw up the entire reconstruction, right? So one outlier point might also be a problem. So maybe take this with a caveat. So they're also not as good with outliers in a sense. Okay, so in practice, you can think about finding these are kind of two extremes, right? One is a local method, one is a global method. So one thing you can do is you find a good compromise between local and global fitting. You can fit point clouds in a coarse-to-fine manner. You can do it based on segment point cloud in the parts first, and then fit individually, stuff like that. So there are a lot of different options. I mean, I wanted to share a few of them. There's a couple of methods that go basically further here. There's radial basis functions with floating centers. Basically, the idea is to reduce the number of centers, but also optimize them jointly for the center positions. This becomes nonlinear, but it's more flexible and doesn't need as many centers anymore, which is good from basically with fewer points, you can represent more complicated stuff. There's this cool paper by Jochen Süßmuth. It's a surface reconstruction based on hierarchical floating radial basis functions. So they kind of combine these ideas, and that's a very cool method for radial basis functions. There's another way to do implicit surface reconstructions, which is pretty similar to what we have just learned. It's similar to this matrix even, and this is called Poisson surface reconstruction. And here the idea is basically you having an indicator function. The indicator function that says it's basically it's 1 inside, 0 outside, and the gradient is basically there's only a non-zero gradient on the surface. It's a kind of a different thing. So basically the surface is defined by the gradient of the manifold here. So if the indicator function here is 1 inside and 0 outside, then the only gradient that is non-zero is on the surface, right? And this can be optimized by solving a Poisson equation. Now, I don't want to go into more detail here right now, because that is the paper that I'm going to give you as homework to read. I'm going to share you the link at the end of the slides. But this is something I would like you to have a look at, because Poisson surface reconstruction is a very, very popular method, and I want you also to get a bit of an exercise in looking at or reading academic research papers. So this is probably a very important task to do, because that's something that a lot of people use in practice. Okay, so now this is now we've talked a little bit about surface representations. We've even talked already a little bit about reconstructions. I wanted to talk a little bit about some properties of sign distance fields, or sign distance functions. And one thing I've already mentioned, it's not so straightforward to make use of sign distance functions. So one thing we would like to do is, we would like to be able to render a sign distance function, right? And there's basically two ways to do that. So if you have a sign distance field, one option you can do is you can raycast it. That's what we're going to do first. And the second thing what you can do is you can actually convert it back into polygonal triangle mesh. That's also what we're going to do, but that will be the second part. Okay, but the idea of rendering is straightforward, right? Just to give you, graphics people obviously know it, right? You have a camera, you have an image plane, you shoot a bunch of rays, and these rays intersect the surface, and you want to determine what is the pixel color or depth value on these surface points, and then you're writing the surface point value, the color of the surface point value, you're writing it respectively at the pixel location. So that's what we want to do right now. So we want to have a sign distance field, and we want to figure out how to render it with a raycast. And how does it work? Well, let's say this here is our sign distance field, right? It's everything here is positive, that is outside the surface, and everything inside here is negative. And every point on the surface, every point on the distance field, or every query on the distance field, tells you how far away you are on the surface, right? So this one here will, like, basically, if you are here, this is 0, right? This would be 1, this would be 2, this would be 3, and so on. So this is a distance field. So the sign tells you what is the shortest point to the surface. Okay, so if you want to rasterize this whole thing, or if you want to raycast this whole thing, the way you do this is you set up your camera position and you're shooting a ray. And now you can do a thing called Raymarch. So what you do is you're just going ahead and going step by step along this ray, and all you're doing is you're checking if the previous sample point was positive and the next sample point on the ray is negative. Because if that happens, then I know, oh, I must have crossed the surface. Right? So positive, 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 negative, and now I know, oh, there was a sign change, and because of the sign change, I know there must be the surface. Okay. Now, if you're doing this with a fixed step, you actually, it depends, right? If my step size here is too big, I might actually do this, 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 and this, and I'm not getting a good approximation where it exactly is. So there's a few things now you can do. One of them, you already can do a linear interpolation, right? So basically, you know the distance value here, you know the distance value here, and now you interpolate linearly between these distance values. That tells you, oh, a much better approximation where it is. It's neither here nor here, but it's somewhere in between. You can even do other things. You can even do a binary search, right? So you can sort of say, oh, it wasn't here, but it was in between. Let's check here. Oh, it's not in between. It must be here, and so on. So you kind of successively refine with the binary search. And every time you do it, you can do this linear interpolation when you make the respective lookup values. This is the basic ray marching method here, right? So again, sign change, and then you do a linear interpolation, and then you find it. Again, this is not that easy because the linear interpolation will not exactly give you that point. This is kind of an easy thing. So you can do binary search and stuff like this to find the accurate thing. Not so easy to find it accurately because the distance fields, they only tell you not along the ray direction where to go, but they tell you just absolutely what the shortest path to the surface is. Okay. You can do also dynamic. So the obvious thing here, this is super slow, right? So the question is, can we speed this up a bit? And yes, there is. And this is a thing, you basically can change the step size, so what we just seen here, right? Like the step size here along the ray, right? We can just dynamically adapt and maybe make bigger steps when we know there's no surface. And this is the nice thing about the distance fields. With the distance fields, we know when we can make big steps. And this is a thing called sphere tracing, right? So sphere tracing means you know the step size and set it according to the distance values. And why according to the distance values? Well, the distance value in the sign distance field tells you the closest surface is that distance away from you. It doesn't tell you the direction necessarily, right? But it does tell you if you have a distance value of 5, you know that there's no surface that is closer than 5 to it, because otherwise the distance value would be smaller, right? So what you do now is here, you take a point, you check out the distance value here, right? The distance value was probably somewhere to this is probably the closest surface, right? This defines a radius. This is this sphere here, because this was the closest distance here, right? This is the distance value you looked up here. And you know now that because this was the closest distance, you know it's not possible to have any surface value closer. And what that means is, well, we can make a pretty big step right now. We can basically step to the sphere. Maybe the surface is here. Maybe. Maybe it's not. We don't know that for sure, right? That's not what the distance field. The distance field just tells us, okay, we can make a step that is safe as long as we don't go further than the distance value. So we go the distance value, this is one step. That's what we can save. And then we look up the next distance here. We look up the distance at this point now. Again, this defines another sphere. This is like the closest point here, right? So what we do is we step to the next value, right? Now we're here. Now we check the distance value here. This is this sphere here, right? Now we do another step, going to here. Still haven't found the surface, right? Everything's still positive. Check the next distance value, that's this one, so it defines this sphere. Next one, it's here, and so on, right? So next sphere, look up the distance value. Next sphere, look up the distance value. Next one. And now the good thing is you can just continue until you're below a threshold, right? And once this distance value is basically close to 0, we know that we found the surface. That's good, right? This is field tracing. So when everybody tells you how to do raycasting in a distance field, that's how you practically should do it, right? So distance fields are very useful. In practice, you don't need a lot of steps. Worst case scenario is if a ray goes in parallel to the surface, basically, right? If a ray goes in parallel to the surface, then it's pretty bad because then the steps are pretty small. Optimal thing is, if I have a point here and I shoot a ray in this direction, that one I can do in O of 1, right? That's just one shot. Because there's no other surface that was closer than the surface across the point. So if the ray is orthogonal to the surface and there's no other surfaces left and right basically to it, that's the best case. And the worst case is if the rays are parallel to the surface. But this is pretty useful because that means you can actually raycast these things very fast and efficiently. Okay, so that's the first part, how we can render it. We can go ahead and raycast it. Well, and obviously once we hit it, we know the surface point, we know the camera distance, we can evaluate possibly the color here and so on. Okay, so this is how we raycast it. The next thing I told you is we can also not raycast it and say we're converting the isosurface into a polygonal mesh. Well, then we use the polygonal mesh that is easy to render, and we can use it for all kinds of other things what we have previously seen with our polygonal meshes. So one thing that we will often have as a task, you have basically laser scan as input. From the laser scan, we're gonna create an implicit function like a sign distance field, and then we want to recreate an OBJ file out of it, apply file that we can actually store as a mesh, right? And there's a method called marching cubes. It's actually it's a relatively straightforward kind of a brute force method. This method is already ancient, right? Like many people have done this for isosurface level set extractions, and the idea is basically you convert an isoline of a bivariate scalar to a polygon, and I want to show you this quickly how this basically works in 2D. So let's say this is a 2D sign distance field, right? This is a 2D sign distance field, right? These are the sample points in your 2D grid. These are all the distance values, right? Some distance values are -1, some distance values are +2. So this one is 3, 2, -3, and so on. So now what can you do here? Now what you do is, for every cell here, you're checking these cells. You're gonna check if there's a zero crossing, right? So if I'm looking at this cell here, I have some values that are negative and I have some values that are positive. Correct? Now, if you look at this cell here, you already know that if one negative value is negative and others are positive, you know there must be a surface in it, right? And you just look at the signs here, right? Negative, positive, positive, positive. And now what you do is, you know which vertex is it of the cell. Okay, so this is negative, this one is positive, that means there must be a surface intersection here somewhere. Here, and this one must also be a surface intersection somewhere. Between these two, there's none, and between these two, there's also none, right? So now within these cells, we know that here was a surface intersection and here was a surface intersection. So you connect these 2 points. And where to connect them depends on the actual distance value. So this is a -1 and a 5, so it means it's closer to the -1 as the isosurface, right? And now what you do is, well, we can show that, right? So this is basically, now we know, oh, there must be a surface here. So we just insert the surface. This is based on the interpolant here, on the interpolating function here, based on the actual values, and the signs tell you whether there should be a value. Now we go to the next cell. We go to this cell here. Now what we do is, here's a minus, here's a plus, minus, and a plus. That means, okay, we know in this edge, we're going to have a surface. We are going to have a point here somewhere. Between these, we have a point here, and between this one, we also have a point, and between this one, we also have a point. And now we know, oh, this one was negative, so it has to be connected here because it's on that side of the cell. This one is connected on that side of the cell, right? And so on. And this is what you continue everywhere. And eventually, you know that this is going to be a surface. There's a surface here, there's a surface here, and there's a surface here. Again, this is in 2D. And the way you do this algorithmically is by brute force. What I just described to you is basically a table lookup. So all you're doing right now is you check this table out, and you check what is the combination of positive versus negative signs, and then check out what is the respective values of the distance values to know where the intersections happen, and then you connect them accordingly, right? So in 2D, you have, for one cell, you have 4 corner points. Each corner point can be negative or positive. That means there's 2 to the power of 4 possible combinations here, right? So it's 16 possible combinations of how, for one cell, these intersections can happen or not happen. And this is a table. And based on this table, you know where and how to create the respective polygons out of it. Now you can do the same thing in 3D. Similar idea. Now we convert an isosurface of a trivariate scalar function into a polygon mesh. Same thing, giving uniform sampling on a 3D grid of the implicit function. And for every grid cell, we determine the zero crossing. Now instead of this 2 to the power of 4 combinations per grid cell, now we have 8 corner points per voxel. That means we have 2 to the power of 8 possible combinations. How triangles can lie within a cell. Yeah, and then how do we do it? We just do a lookup table, right? And then we adjust the vertex position according to the linear interpolations, what the actual distance values are. Okay, now we have this big lookup table. Practice looks something like this. So we basically check, oh, for instance, this one was negative, then we know, oh, there's a triangle here. This one negative, then we know this one must be here, and so on, right? Same thing as in 2D, except now we're creating triangles rather than line segments in 2D. And then the linear interpolation is straightforward. This just depends on, so if this is the -1, this is the 5, then we know the intersection must be somewhere here. This is just the linear interpolation. Okay, in practice, this can be actually parallelized, right? You just do this independently for every voxel. Actually, it's the dual graph of the voxels, right? If you think about each voxel stores a distance value, then the cells where you run marching cubes on is actually the dual graph of that. So this marching cubes grid looks something like this in 3D. So it's this edge table of 256 entries, right? And then you have this triangle table of 215 times 16 entries, right? You can check this table.h out. If you want to implement marching cubes, you probably want to start with that file in 3D because that one to do on your own is a bit annoying. Let's put it this way. Doable, but annoying. Okay, this is marching cubes. Marching cubes is probably, it's not super elegant, I guess, but it's probably one of the most used algorithms in this area, right? I mean, from a pure paper citation standpoint, this is a very popular method. Okay, so this is mostly it for now. So I'm almost through everything what I wanted to do today. I wanted to announce a few administrative things. One thing I already mentioned during the lecture. I would like you to have a look at the Poisson surface reconstruction paper by Misha Kastan. Here's the link. You can also Google it. You'll find it, I'm sure. There's a follow-up paper, Screen Poisson surface reconstruction, that does a little bit more stuff. So I want you to have a look at these 2 papers and try to understand them with the knowledge you've gained today from the lecture. And I hope this should be doable at this point. And I also want you to actually take this a bit seriously because I think it's really important that you gain a bit of exercise reading academic papers. So please have a look at this one here, at these 2 papers, read them, and a fair warning, I might ask some questions about it in the exam afterwards. So yeah. This is very popular reconstruction method, and I want you to get a bit of exercise in reading papers. Okay, all right. Then next week, we're gonna continue with 3D reconstruction methods, and we're gonna apply more of these things that we discussed today, and we're gonna do a lot of cool things. All right, see you next week. Enjoy reading the papers.